Let's talk about probabilities, also represented just by a small case p. Probabilities have to do with the mathematical chances that things are going to occur. So let's take a simple coin, heads, tails. If I flip this coin, what is the probability going to be that I'm going to get a heads? There are two sides to the coin, a heads and a tail, and there's only one head that I have to choose from. So the probability is going to be 0.5. Flip the coin. I got a heads. Okay, no reason for me to run out and buy a lottery ticket. I had a 50-50 chance. Alright, now, what is the probability that if I flip this coin again, that I'm going to get a heads? Now, a couple things we need to realize here. I'm not trying to predict in advance what's the probability of me getting 5 heads in a row. Okay, I've simply already flipped the coin, that's done. I'm going to predict what the probability is of me flipping this coin and getting heads again. Now, what we have to realize is that inanimate objects do not have memory. So they don't remember what I just did, and they have no way to influence what I do next. So the probability that I'm going to get heads on the next flip of this coin is going to be 1 divided by 2, or 0.5. Okay, again, I got a heads. If I flip this coin again, the question becomes, what's the probability that I'm going to get heads a third time? Again, I'm not predicting the probability of getting 3 heads in a row. I'm simply just saying, I'm flipping this coin and I want to know what the probability is that I'm going to get heads. It's going to be 0.5. Tails. The streak is broken. Okay, so let's look at other chances or probabilities. This is a 12-sided die. It has 12 different facets or faces on it, each numbered sequentially 1 through 12. What am I doing with a 12-sided die? You don't really want to know. What's the probability if I roll this that I'm going to get a 7? Okay. There are 12 chances of me getting a 7 because it has 12 faces to it when I roll it. There is only one 7 on the die. So my probability is 1 divided by 12. Roll the dice. I got a 12. Let's look at probabilities now associated with different things that can happen in a deck of cards. I have a standard deck of cards here, 52 cards in the deck. Okay, you can see here, as I fumble with the deck, that is a standard deck, 52 cards in it, and I'm going to shuffle the deck. Cut it. Alright, what is the probability that I'm going to get the ace of spades? Okay, the probability of getting the ace of spades, there is only one ace of spades, and there are 52 cards in the deck. The probability then is going to be 0.0192. I turn over the top card, it's a 4 of hearts. Not my lucky day. Alright, let's remember this card, 4 of hearts. If I replace this card to the deck, and then I shuffle the deck, cut it a couple times, what is the probability that I'm going to draw another 4 of hearts? It's 1 divided by 52. The deck has no memory, or 0.0192. Ace of hearts. Alright, if I do not replace the ace of hearts to the deck, what is the probability that the card that I'm going to draw next is going to be an ace of hearts? Well, that probability is going to be 0 because there is no ace of hearts in the deck. let's look at some of the other probabilities. If I shuffle up the deck, replace all the cards to it, what is the probability that I'm going to draw a red card? Well, there are 52 cards in the deck, and the deck is split evenly between red and black cards. So there's 26 red cards in the deck. So the probability of getting a red card, this will reduce to 1 divided by 2, or the probability would be 0.5. Black card, really unlucky day. Not even with the flip of a coin. Now let's say I draw a red card from the deck. What is the probability that the next card that I'm going to draw is going to be a red card? Now I'm not going to replace this one. Shuffle the deck up and cut it. Now the probability is going to change slightly for a couple reasons. One is there are no longer 52 cards in the deck. There's 51 because one of the cards is no longer in the deck. In addition to that, I've already taken one of the red cards out. So there's only 25 red cards remaining out of 51. The probability is going to change slightly now to 0.49. Second red card. Something finally worked. Let's look at a couple of other probabilities now when we try to put things together in multiple successions. But first I want to do one more probability related to a specific card type in the deck. Shuffled it up. What would be the probability of drawing a queen? Alright, well there are 4 queens in the deck. Queen of hearts, Queen of clubs, Queen of spades, Queen of diamonds. So there are 4 queens out of 52. Probability there then would be 0.077. Didn't hit it. Okay, let's look at multiple events. Shuffling the deck. What would be the probability that without replacing the card that I draw first, that I will draw an 8 of hearts followed by a black card? Alright, so now I've got to actually derive a mathematical equation and bring these probabilities together. So the probability of drawing an 8 of hearts, there is only one 8 of hearts in the deck out of 52. But not only do I want to draw 8 of hearts, but the very next card that I draw, I want to be black. So I want the probability of doing this and this. Now whenever we use an and, we're going to use a multiplier in a probability equation. And the way that I think about that is that the probability of doing this combination is going to be more remote than doing any one of these two things. So my number is going to get pretty small. The probability of getting a black card, okay, this is red. That means that there's 26 black cards that will remain in the deck. But there will only be 51 cards in the deck because I've got one card sitting out. I solve this equation, and that would be 26 divided by 2652, or that would reduce to 1 divided by 102. Probability of that would be 0.0098. So a pretty remote probability that I'm going to take a deck of cards and first draw an 8 of hearts, and then a black card. But I gotta try it. Up, queen of spades first, followed by a black card, 7 of clubs. All right, let's look at one more probability here. Okay, and this time I'm going to make an operation with replacement. All right, so again, the question is here can be slightly different. What is the probability of drawing a 9 from the deck and then with replacement of the original card drawing a club? Alright, so we're going to calculate the probability. The probability of drawing a 9, remember there's 4 nines. 9 of clubs, 9 of spades, 9 of diamonds, 9 of hearts. The probability is going to be 4 divided by 52. I'm going to replace the card to the deck, and the probability of drawing a club, remember there's 4 suits, so 52 divided by 4 is going to be 13 divided by 52. We'll solve this to equal 52 divided by 2704, which reduces to 1 divided by 52, or 0.0192. Okay, so the first card from the deck I draw. Alright, I got lucky there. A 9. Alright, so the probability then, next that has to happen, I replace the card to the deck, shuffle the deck, next would be the probability of drawing a club. A club. Actually, I fixed the deck and put a 9 and a club on top of it. But again, the illustration, so here, just to show you how remote that probability would be, I'll really shuffle the deck. Even cut it on camera. 2 of clubs, 10 of spades. Goes to show my luck. So hopefully you gained a little bit of understanding about the mathematics of simple probabilities. This will help us to set the foundation to talk about p-values. That's been your Statistical Minute. Also, how to fix a deck.